So in this video, we are going to be looking mostly at section 2.6 in digital design by Mano and Saletti. We are going to cover just the tail end of 2.5, which is De Morgan's theorem. So before we start this, I wanted to take a moment and to get an idea of where we are and where we're going. So in order to do that, let's look at the objectives of the chapter. So the objectives of this chapter have in 2.1 through 2.5, basically, we covered 1 through 4 of these. And in 2.6, we're going to be covering, well, actually, this is actually still in 2.5, but we're going to cover that just real quick. But in chapter 2. In section 2.6, you cover a lot of material. So this is what we're going to cover. So let's go back. So we just got, in the first, we just got a general understanding of postulates and how they related to algebraic structures. And then we specifically looked at the Huntington postulates. And we took a table out of this so that we could use some of the basic postulates. Okay, so it says understand the basic theorems and postulates of Boolean algebra, and we had a table and we've been looking at that. The next thing we did is we from a Boolean function, we learned how to create a logic diagram from the Boolean function. Now, know that when we were doing this, we were minimizing these Boolean functions using Boolean algebra so that we could create the least amount of gates to get our output. So we're done with that, but that's where we are. So now we're looking at, we're going to do De Morgan's theorem real quick. And just so you know, and keep in your mind that De Morgan's is used when you want to find the complement of a function. Okay, a Boolean function, you can use De Morgan's theorem. Okay, and so we're going to be doing that. And then we're going to look at, I'll go on to what some of these things are later. There's a lot of vocabulary in here, and I'm going to try to get the concepts down before we start doing this vocabulary min terms and max terms and how to convert them and whatever. So we're going to do that in a minute, but we're covering 6 through 9, and then 10 I'm going to leave separate, and we'll get to that afterwards. So this for us is for homework. This is for homework. It's Unit 2, Part B, but it's the homework number 2. Number 2. Okay, so let me just clear our screen. And let's move on to this next slide. So this next slide real quick is talking about De Morgan's theorems and the fact that they are used to find the complement of a function right here. They're used to find a complement in a function. So this means that all zeros would become ones and all ones become zeros. So this is done for functions by using De Morgan's theorem, and you can see them in table 2.1, they're theorem 5, and they're listed here below. But what it means is if you have the sum of x plus y, and you take the prime, you would get x prime, y prime multiplied. Or you can think of this as an or and an and, okay? And then B says if you have xy multiplied and you take the prime, that equals x prime plus y prime. Now, on page 54 in your textbook, it shows you that this can be extended to 3 or more variables. And they do the proof for extending it to 3, but it also can be extended to more than that if you want to. So if you want to think about it, though, because you can add more variables, that there is a generalized form of doing De Morgan's that states that the complement of a function is obtained by interchanging all and or operators, and then taking the complement of all the literals. So examples of this on page 54. I think that you will be fine with this. It's not that hard. So I'm going to leave that up to you to work through those examples. So what I wanted to work on is clear all drawings. What I wanted to work on is 2.6 today. So here is your review. Up on top here in 2.5, okay, we learned to take a Boolean function and make a logic diagram. Now, I'm just going to make this a real simple case, but if you had x, y, right, and you wanted to write this as, you want to do a logic diagram, you would be taking this, you'd be making an AND gate, you'd say x, y, and you have some output. Okay, now that's really, really simple case. We also have been using truth tables. So in this case, you have x and y, and then you have your output. And so you could have, to get all possibilities, you go like that. And in an AND gate, you know that both inputs have to be positive to have a positive output. So if you think about it that way, you won't get in trouble. Now, I want you to notice, because this is going to come in handy here, is that whenever you look at the number of variables, and this is 2, right, that you know that the possible amount of combinations of input is 4. So if you were to go to 3 variables, know that the possible amount of inputs that you're looking for are 8. And if you went to 4 variables, the possible amount of inputs you would be looking for, the combinations would be 16. Okay, so so in there, you took your Boolean function, you made your logic diagram. We've been using truth tables. So now in this section, so here we did the Boolean function and we created a circuit, right? Now what they're doing is this Boolean function to the circuit is still there, but in this section, you're going to learn to look at a truth table, be able to come up with a Boolean function, and then draw the circuit. So they're adding an extra step here. But before we go into all of that, what I want you to think about is what you know. And you know, if you were to look at this table, and we're looking at function 1, that in order to have a 1 on the output, there's only 3 cases, right? This scenario would create a 1. This scenario would have a 1 as an output. And this scenario, right, would have a 1 as an output. Now for this, I want you to think, when I'm doing this, that x means a 1, and if I have the complement of x, that we're doing a 0. But if you were to think about this and to go into a diagram, what would this mean? Well, this would mean, for the first scenario, right, you would need an AND gate, right? You would need an AND gate. Now the z is already a 1, so you can just bring in the z, right? That's z. But for x and y, in order for them to be 0, right, you would have to be taking the negative of that. So, or the opposite of that. So if x is positive, right, if the x is positive, then when you come in here, you can just invert it. And by the way, when you do this, you can just draw a bubble on the input, okay? So that's what you need for that input. And then z is also equal to 1. And your y, if it's equal to 1, if that's the way you're looking at it, then you are going to invert it to come in here. So now, oh, sorry, I should have said, in this case, x and y are 0. So this x and y is 0. You need them to be 1s, right? to go into your AND gate so that all of them can be high and you can come out here, right? So for our logic diagram so far, you would have that gate. That gate would give you your output of 1 that you're looking for. Let me just erase a little bit of this. That would give you the 1 for an output. Okay, so then the second scenario that you're looking at is that you have, we're not going to worry about how this is coming in, but your second scenario, you're having a 1 on the X, right? And you're going to have to invert the Y and the X, right? Because if they're coming in at zeros, you want them to be 1s to get your output at 1. And then the last gate that you would need is these are 1, 1, 1. And so if these are all coming in as 1, then you're all set, right? That would give you a 1. So now what would you do with this? You would say, well, if any one of these scenarios work, then I can put this into an OR gate. If any one of those works, then the one of these inputs will be high and I will get my 1 as an output. Now, you don't worry about all the other cases because all of them are not going to give you a 1 anyways. So you do not need to be putting their inputs into this OR gate. I hope that wasn't too confusing. I just want you to think about that you can look at a table and that you can say, okay, what's going to give me the 1 for an output? Okay, well, it's the combination of 0, 0, 1, 1, 0, 0, and 1, 1, 1. And then you say, well, how would I get that if I was putting those into AND gates, right? Well, in this case, the first case, right, the X and the Y would have to be inverted because they're coming in as zeros. So you'd need them to be 1s. In the second case, your Y and Z are coming as zeros, so you'd need to invert those coming into the AND gate. And in the last scenario, they're all 1 anyways. And then if any one of these criteria are met, right, any one of them, then your function, your output to the function is going to give you a 1. So you can put these inputs into function, right? So if I were to look at this and try to write a Boolean equation out of this, I would say, well, if I have, you know what, I'm actually going to leave that for the next video. So, but it shows you these are the inputs that are going to give you a 1, right? So any one of those will give you a 1. So we did the zeros. How could these gates be represented in a Boolean list? I think what I was looking for is this first one would be the complement of X, the complement of Y and Z, right? And if you did the next one, it would be X, the complement of Y and the complement of Z. And the last one would be X, Y, and Z, because you did not have to invert any of them. And if they're all going into an OR gate, you could just go like that. So we're going to be going over this in more detail, but I thought that that would be a good start for you just to be looking at a truth table and say, what does it take for me to get a 1 as an output in this scenario?